So in this video, I want to do two things in this video. First, I want to do a little bit more on how these hybrid orbitals come into being, the creation of these hybrid orbitals from atomic orbitals. And then, secondly, we're going to do an example that shows how to describe all the electrons in a molecule example in a lot of detail. But first I want to do a little bit with our creation of these hybrid orbitals. So we're going to start with two electron groups. And we're going to start this kind of same thing we did in the previous video, but I kind of want you to see it from scratch without so much on the screen for each case. So going through those guidelines that we talked about before. If I'm going to start with two electron groups. If I'm dealing with two electron groups, well, on the right hand side I'm going to make my hybrid orbitals. So two electron groups means I need two hybrid orbitals. I'm going to get my two hybrid orbitals in here. Well, how am I going to create those hybrid orbitals? Well, two electron groups means two hybrid orbitals. Two hybrid orbitals means I need to use, on the left hand side, two atomic orbitals as well. Well, now I have my two atomic orbitals. Now we have to talk about the identity of these atomic orbitals. So I'll always start with the S, then we're going to go to our P. Because I used an S and a P, this hybridization, these hybrid orbitals are going to have some of that character. So we get our sp hybrid orbitals coming out of that. Two electron groups, sp, these are going to come in that linear geometric orientation again. We get that linear electron pair geometry coming out of that. Now I'm just going to continue this pattern to go all the way through the 6 as well. So now if we do this for three electron groups, well, three electron groups means I now need three hybrid orbitals. Well, three hybrid orbitals had better come from three atomic orbitals. Which atomic orbitals should I use? Well, always start with the S, then go to your P's. Remember, for some of these I'm going to have leftover P's that are unhybridized. I'm holding them in reserve. I have one in reserve here. Previously in the two electron groups you saw I had two unhybridized P's. What are the hybrid orbitals going to look like? Well, we're going to get sp2 hybrid orbitals based upon the 1s and the 2p atomic orbitals that we had to use for this. Three electron groups, sp2 hybridization. These are all going to be situated in that trigonal planar electron pair geometry. We can go on and on with this. Here's three electron groups. If I go up to four electron groups, four electron groups means I need four hybrid orbitals. Add a hybrid orbital, that means I need four atomic orbitals, using those guidelines. What atomic orbitals am I going to use? Start with an S, then go to your P's. What will be the identity of these hybrid orbitals? Well, because it came from an S and three P's, I'm looking at sp3 hybrid orbitals. Four electron groups, sp3 hybridization. These are going to be in that tetrahedral electron pair geometry, and I'm going to get my 109.5 degree bond angles coming out of that. We keep on going up, and I do five electron groups. Take off the previous one. Five electron groups now means I need five hybrid orbitals. That was that first guideline. Well, five hybrid orbitals have to come from five atomic orbitals. That's that second guideline we've been talking about. What's going to be the identity? Well, start with an S. I have one S. I have three different P's that I can use. Now I'm out of p orbitals, so now I have to use d orbitals. And we know we have to have d orbitals anyway when we're expanding beyond the octet anyway, which is what happens with 5 electron groups. The third guideline is the identity of the hybrid orbitals. They're going to look like whatever atomic orbitals you use to create them. In this case, it's an averaging of an s, 3 p's, and 1 d. So we get our sp3d hybrid orbitals in here. These are going to be arranged in that trigonal bipyramidal fashion with the equatorial and axial positions. You're going to get 90-degree angles, 120-degree angles, and those 180-degree angles coming out of that. If we show how our hybrid orbitals get created for our last type of electron group, that's when we have 6 electron groups. 6 electron groups means I need to create 6 hybrid orbitals in order to really explain what's going on. Put another orbital, 6 electron groups, 1, 2, 3, 4, 5, 6 hybrid orbitals. That means 6 atomic orbitals have to be used. 1, 2, 3, 4, 5, 6. Which atomic orbitals do I need to use? Start with an s, then use your 3 different p orbitals, and then your last orbitals you'll have to use d orbitals in order to get up to the number that you need. So what type of hybrid orbitals get created? Well, the atomic orbitals used were an s, 3 p's, and 2 d's, so our hybrid orbitals are sp3d2. That's the type of hybrid orbitals that get created from this. So again, very similar to what we saw in a previous video. I just kind of wanted to show it to you fresh and clean, kind of on a more blank slate, so you could actually look at what's happening. Now what we want to do next is we want to do another example of describing the electrons in a bond. You had one in the packet that we already did in a previous video, but I want to do another example of this. So we're just going to check and make sure everything's still in view here, and we're still looking okay with this. So using those guidelines from the handout, what we're going to do is we're going to go through and we're going to describe all of the electrons in this molecule to a high degree with a lot of detail. So what I recommend you do is I recommend you pause this video, try to do this yourself. Pause the video, take 10 minutes, try to go through this and see what you could do on your own for this. And then resume the video and we'll go through it and you'll see how well you did on this. So this is an opportunity for you to check yourself on this to see how you're doing. So highly recommend you pause the video, try to do it yourself, and then check and see how you did based upon resuming this video. Alright, so I'm going to assume you actually did that and you did pause and try this on your own. We're going to look at all these different electron groups. The first set of electrons we're going to look at is this lone pair on nitrogen. What can we say about that lone pair on nitrogen? Well, that lone pair on nitrogen, we know lone pairs come from hybrid orbitals. But we got to be a little bit more specific. They're going to reside in hybrid orbitals, but what type of hybrid orbitals are there going to be? So we need to figure out what the hybridization is of that nitrogen. Well, to do that, we got to look at how many electron groups. So how many electron groups does the nitrogen have? Remember, this is the VSEPR counting. A double bond or a triple bond only counts as 1 electron group. So here's 1 electron group. This is the second. So we're looking at 2 electron groups. So when you're dealing with 2 electron groups means sp hybridization. So in detail, what we would say is the lone pair on the nitrogen resides in an sp hybrid orbital. Take kind of that highlight away. And now let's start talking about the bonding between the carbon and the nitrogen. I see a triple bond. Anytime you have a multiple bond, only one of them is going to be a sigma bond. The other ones are going to be a pi bond. So in this triple bond, one of them's sigma, two of them's pi. Let's start with the sigma bond. So I'm going to just start with the sigma bond. You can start with the pi bond. Doesn't matter which one you deal with first, as long as you recognize of these three, one sigma, two are pi. So sigma bonds we talked about as the overlap of hybrid orbitals. Well, what kind of hybrid orbitals do we have? Well, it's going to be a hybrid orbital from nitrogen and a hybrid orbital on carbon. We already decided what the hybridization of the nitrogen was. We said it was sp from two electron groups. So now we just got to figure out what is our hybridization of that carbon. So we're going to count the electron groups on the carbon. Remember, this only counts as one electron group, this triple bond. So 1, 2. This carbon only has two electron groups in our Vesper counting. Two electron groups is going to be sp hybridization. We already decided the nitrogen was sp hybridized, or had sp hybrid orbitals. So what can we say about the sigma bond? This sigma bond is the result of the overlap of the sp hybrid orbital on the nitrogen with the sp hybrid orbital on the carbon. That's how that sigma bond came into being. Now let's talk about these pi bonds. Remember, two pi bonds here. Of those three, just one of them is that sigma bond that we already discussed. Two of them are going to be pi bonds. So whenever we talk about pi bonds, we want to decide, is it localized or delocalized? And the way we determine that is we look at, are there resonance structures? So when you look at this Lewis structure, are there any resonance structures that you could reasonably draw for this? And when you look at this, you're going to say, well, no. There are no good, reasonable resonance structures here. This is the only resonance structure that we really have that we could draw. Anything else you would try to draw wouldn't make much sense. So what that means is these pi bonds are localized pi bonds. So that's the first thing we can say. We said pi bonds result from the overlap of unhybridized p orbitals. So remember, this nitrogen is sp hybrid. That means I have two unhybridized p orbitals. This carbon was sp hybrid orbital. That means two unhybridized p orbitals. These two pi bonds are going to come from the overlap of those unhybridized p orbitals on nitrogen with those unhybridized p orbitals on the carbon, and they're going to be localized. So now we dealt with those electrons. Now we can look at the electrons that are involved in the carbon-carbon bond. So that's a single bond, so we want to deal with that as a sigma bond. Sigma bonds we want to talk about is coming from overlap of hybrid orbitals. So what kind of hybrid orbitals are we looking at? Well, we already dealt with this carbon. We said that was already sp hybridized. What's going to be the hybrid orbitals on the carbon on the right? Well, let's count the electron groups. 1, 2, 3, 4 electron groups. 4 electron groups will match up with sp3 hybridization. So this carbon in the middle, sp hybridized. This one, sp3. So what we would say about this bond is this is a sigma bond that results from the overlap of carbon's sp hybrid orbital with this carbon's sp3 hybrid orbital. So the next things we could look at, these would all be the same. These would all work the exact same way, would be the bond between the carbon and all of the chlorines. What we would say about one, we could say about all of them? Well, it's a single bond, so that means it's going to be a sigma bond. So we can definitely say that. Sigma bonds come from the overlap of hybrid orbitals. Well, what kind of hybrid orbitals do we have? Well, we already talked about the carbon being sp3. What kind of hybrid orbitals do we have on the chlorine? Let's count the electron groups on the chlorine and find out. 1, 2, 3, 4 electron groups. That means the chlorine will be sp3 hybridized, sp3 hybrid orbitals. So this carbon has sp3 hybrid orbitals. The chlorine has sp3 hybrid orbitals. So if we're describing this bond, we would say this bond is a sigma bond that results from the overlap of carbon's sp3 hybrid orbitals with this chlorine's sp3 hybrid orbital. And what we could say about one, we could say about each one. The last type of electrons that we would be looking at would be the lone pairs on the chlorine. Lone pairs reside in hybrid orbitals. So being lone pairs reside in hybrid orbitals, we just have to say, what kind of hybrid orbital is that lone pair going to live in? Well, we already previously decided that chlorine was sp3 hybridized because of the 4 electron groups. So if we were trying to describe these electrons in as much detail as we could, we would say these electrons reside in sp3 hybrid orbitals. So I want to give you another example of how to look at a Lewis structure of a molecule and electron group by electron group go through and in great detail describe what's happening, how much detail can we describe for each set of electrons that we're looking at.